It's the longest bridge of its kind, with a single span leaping almost half a kilometre and a roadway that plunges into a record-setting tunnel. The vision is bold. The challenge is extreme. The plan audacious. It's a bridge that will change the map of Europe. What does it take to build one of the world's mega bridges? northern Europe, the Baltic Sea converges with the North Sea at the Øresund Strait, a 16-kilometre wide stretch of water with notoriously lousy weather that separates Denmark and Sweden. The Øresund Strait is a frustrating barrier because each shore has something the other needs. Copenhagen in Denmark needs cheaper housing. Malmö in Sweden needs more jobs. If the two cities could be connected, they could form an economic powerhouse. A bridge would make them one big metropolis. But a bridge has never been possible, until now. The Øresund Bridge is the world's longest cable-stayed bridge. It can carry cars as well as the enormous weight of trains. 1,090 meters of road and rail dangle from 160 cables. 60 meters above the sea. The support towers soar 204 meters into the air, making the Øresund Bridge one of the tallest cement structures in Sweden. The height is the equivalent of a 60-story building. This awesome project officially started in 1991, when the Danes and the Swedes agreed to connect their countries. It was a difficult pact to negotiate, and the subsequent work would only get harder. Companies from both countries formed a consortium to build the bridge together. The consortium's first challenge was to work out how to build a 16-kilometre long bridge. Right from the start, they faced a dangerous setback. At the shoreline on the Danish side was the Copenhagen International Airport, Kastrup. Computer simulations showed that building a bridge with high towers would have obstructed air traffic and could have led to tragedy. Building a low bridge would have been safer for air traffic, but then it would have blocked Denmark's ships. Realizing it would be difficult to build over the water, the engineers considered building a 16-kilometre long tunnel under it.
That would be the beautiful solution, build a tunnel from one side to the other, but that would be the expensive solution. So the third solution that we decided was, of course, to build part bridge and then a tunnel where we were getting close to the airport. A bridge would have been easier or cheaper, but would not have been a good idea for the aeroplanes.
But combining a bridge and a tunnel posed a new and serious challenge. How does a tunnel turn into a bridge in the middle of the open sea? The engineers needed to find some dry land where the tunnel could emerge from the water. They needed an island. Unfortunately, no island existed, so they decided to build one from scratch. When it was complete, Denmark had increased in size by 1.3 million square meters. 4 kilometers of tunnel and 4 kilometers of island left 8 kilometers for the bridge to cover. Once again, a low bridge was ruled out because of heavy boat traffic. But there was no airport on the Swedish shore. The engineers could build as high a bridge as they liked, and they needed it to be very high. To clear boat traffic, the bridge would have to stand at least 60 meters above the water, and the center span would need to be more than 450 meters long. To meet these challenges with the best possible bridge, the consortium held a design competition. One of the most spectacular proposals was to build the largest arch bridge in the world.
I think you don't really get an idea of the magnitude of this arch. You might get it from the ship going underneath, but it really is big. It would be a monument of some kind.
But arch bridges have an Achilles heel. As the arch sweeps down towards the water, the clearance for large ships decreases, eventually to nothing.
You always run the risk that a ship could get in there, and therefore you have the risk of hitting the bottom part of the arch, and then the whole thing collapses.
Unable to build an arch, they then looked at building a suspension bridge. Suspension bridge technology enables the longest spans of any design. Two enormous cables stretch the entire length of the bridge, with shorter cables dangling down to hold the roadway. But connecting cables to more cables makes suspension bridges very flexible, and trains can't operate effectively on tracks that bend under their weight.
And railway traffic is so heavy that if you have a suspension bridge, you will find, if you look at it from the side, that the train will always go up a little bulge. It will always going uphill all the time.
Suspension and arch were both ruled out. The engineers then turned to the one design that met all their criteria, a cable-stayed bridge. Its structure is rigid enough for heavy train traffic because the support cables attach directly to fixed towers. And there's a bonus. Cable-stayed bridges are cheaper to build than suspension bridges. Not having the two enormous main cables saves tons of steel. The decision was made. The best design to meet all the Øresund's needs was a towering two-level cable-stayed bridge with a four-lane road on top and a high-speed railroad underneath. It would be a monumental structure, the crowning achievement in the 16-kilometer Øresund link. But the clock was ticking. The agreement between Sweden and Denmark stated that the link must be completed in 5 years. That was 5 years in which to build a man-made island, a record-setting bridge, and the biggest tunnel of its kind. The first priority was the island. This was one of the most critical deadlines. It had to be ready in 14 months. Work began on the 17th of August 1995, when the first of billions of rocks was placed in the middle of the strait. This stone pile would eventually form a 4-kilometer long island, where once there was only water. The first step was to lay the perimeter. Large quarried stones were brought in from Sweden, 1.8 billion kilograms of them. To stay on schedule, material was constantly being brought here, with 16 barges delivering 18 million kilograms a day. Each load was carefully placed using GPS to create a perimeter 12 kilometers long. Then it had to be filled. This was an enormous task, requiring millions of cubic meters of material. And Denmark and Sweden got that material from the bottom of the sea. Phase 2 was dredging. Here the engineers came up with an ingenious win-win plan. Construction crews needed to dredge anyway to prepare for the bridge and tunnel. Now they had a place to put all the rubble. To stay on schedule, crews had to dredge an average of 11.5 million cubic meters every day. This job required the biggest, most powerful dipper dredger in the world, the Chicago. Its scoop bucket is big enough to hold a minivan. Just one pass of its giant shovel can dig up 22 cubic meters of seabed. Its floating platform is so big that parts of the Baltic Sea weren't deep enough for it. It had to dredge a lane for itself, just to navigate the construction sites. But digging was only the first part of this project. Crews then had to transport this astonishing amount of dredged earth. An armada of 50 vessels was assembled. For the pilots, it was dangerous work. It took expert skill to navigate the huge loads, fighting against strong currents, extreme weather, and shallow waters. The single biggest dredging job was the trench for the submerged tunnel. 11 meters deep and 46 meters wide, for 4 kilometers. A total of 2 million cubic meters of seabed. It would have been hard enough to dredge if they were just dealing with mud and stones, but they weren't. 90% was an ultra-hard rock called Copenhagen limestone. Even the Chicago couldn't dent it. So the builders called in one of the most powerful cutter suction dredgers in the world, the caster. The caster's business end is a mega drill bit with 60 cutting teeth, each weighing over 20 kilograms. It's sometimes known as the spinning cone of death. But even with all this firepower, the Copenhagen limestone didn't surrender easily. It destroyed 200 teeth a day. 52,000 were replaced in total. The caster is more than an overgrown drill. It also acts as a vacuum cleaner. As it chipped away the limestone, it sucked up the debris. Giant pumps then forced the stones and water through 4 kilometers of pipeline, all the way to the island. The shards of limestone were so abrasive, they eroded the inside of the pipe. And moving all this rock and mud involved an additional challenge: protecting the environment. The environment is especially vulnerable in the shallow Øresund Strait. The biggest threat is from plumes of debris. Clouds like these can kill huge areas of the seagrass that feeds and shelters marine life. For both Denmark and Sweden, harming the environment was a deal-breaker. They made a pact that if more than 5% of debris was spilled, all dredging must stop. A decision that would put the entire project at risk. 5% spill doesn't sound like much, but it equates to 340,000 cubic meters of misplaced rock. Avoiding spills required a balance of speed and caution, but the dredging workers succeeded in working within their environmental limits. But they were about to face another danger, one that would threaten their own lives. The 25th of November 1995 was the 30th day of dredging for the Øresund link. Digging up the 7 million cubic meters of seabed seemed to be a fairly straightforward assignment, and the crew thought everything was going